In drawing orbital energy diagrams, we made assumptions as to the relative orbital energies. In other words, we assumed which sublevels were at higher energy and which were at lower. It turns out in many cases, we can rank orbital energies using the periodic table as our guide. Let's start by considering the electron configuration of lithium. From its position on the periodic table, we predict the configuration is 1s2, 2s1. Now, why does the third electron choose to reside in the 2s orbital instead of the 2p orbital? Since systems in nature seek the lowest energy they can find, it must be that 2s is lower in energy than 2p. This leads us to the very simple rule that we can state as follows. The sublevels that are in the process of filling must be lower in energy than those that are empty. Of course, this goes for sublevels that are already filled as well. They too are at lower energy than the empty sublevels. This idea becomes enlightening when we look at elements in the fourth period. We saw before how we can develop the electron configuration of an element by reading the periodic table like the page of a book, as in this example for chlorine. If we look at potassium, it is in the S block. Reading the periodic table like a book, we can see that we come to 4s before we come to 3d. That must mean that, specifically for potassium, and by extension for calcium next door, that the 4s orbital must be lower in energy than 3d. If we extend the energy level diagram upwards and add electrons, we would put 4s lower in energy than 3d. The electron configuration then ends with 4s1 rather than 3d1. There would be no reason for us to predict this ahead of time, but the elements potassium and calcium tell us this is so, because in these elements, which have s electrons as their valence electrons, 4s fills before 3d. We can use our idea that orbitals that are filled, or in the process of filling, are at lower energy than those that are empty at any place on the periodic table. In iron, for example, the 3d orbitals are in the process of filling, while the 4p orbitals are empty. Thus, in iron, 3d is lower than 4p. Likewise, if we were to compare the 6s and 4f sublevels in barium, we would find barium on the periodic table, and we would see that 6s is in the process of filling, while 4f, which comes after 6s, is empty. So 6s must be lower in energy than 4f in a barium atom. Again, this is not an order that we might have predicted, but the configuration of a barium atom tells us it is so. As a caution, though, we shouldn't take energy comparisons from the periodic table too far. It only works for sure when comparing empty sublevels with those that have electrons in them. For example, if we look at scandium, it might be tempting to predict that 4s is lower in energy than 3d. After all, 4s comes before 3d when reading the table like the page of a book. We use this very logic to establish that order in potassium. But there, one of the two sublevels, the 3d, was empty. Here, neither sublevel is empty. Note that in scandium, there may be d orbitals that are empty, but the entire 3d sublevel is not empty. So our rule doesn't apply to 4s versus 3d in scandium. In fact, experiments on the electrons in a scandium atom show that 3d is at lower energy. Why should this be? The answer is related to something we've seen before with Hund's rule. Recall the orbital energy level diagram for carbon. Carbon is 1s2, 2s2, 2p2. The 2p electrons spread out with the same spin into different orbitals. We know from Coulomb's law that two electrons with the same -1 charge will interact with a positive energy. If instead of being in the same orbital along the same axis, they spread out into two different regions in space, such that they are farther apart, then the energy will be lower. Why the same spin, you may ask? That has to do with something called exchange energy, which is mostly statistical in nature. We won't go into detail here, but you may see that later in your chemistry career. But how does this apply to 4s versus 3d in scandium? The issue is the size of the 4s orbital versus the 3d orbitals. 4s is much larger. We'll show here one of the 5 3d orbitals. On average, the electrons in 4s will be farther from the nucleus, but also farther from each other. If all 3 valence electrons in scandium are in the 3d sublevel, they are much closer together. And the positive energy from like charges interacting is more significant. Since 4s and 3d are close in energy to begin with, these small corrections based on interaction between the electrons can become significant. If we look at the 4s2 3d1 configuration, it certainly doesn't look like a ground state with empty 3d orbitals at lower energy. But if we look at the 3d3 configuration and include electron-electron interaction, we might visualize that by pushing those orbitals to higher energy. The reason this is confusing is that the ground state is determined by the energy of all 3 of those electrons combined. It might be better to think about the 4s2 3d1 state as having a total energy that comes from the orbital energies and a smaller amount of electron-electron interaction. And compare that with the 3d3 state with a total energy from the orbital energies and a greater amount of electron-electron interaction. What the scandium atoms are telling us is that the 4s2 3d1 state is the lowest energy state. Including the positive energy of electron-electron interaction is a subtle effect, but important because 4s and 3d are close together in energy to begin with. We see that elsewhere in the periodic table, with 5s and 4d, and with 6s and 5d. Complicating matters with 6s and 5d is the fact that 4f is around the same energy. The bottom line is that our original rule of thumb still holds. Reading the periodic table like the page of a book does allow us to compare orbital energies when comparing an empty sublevel with one that is full or in the process of filling. It often, but doesn't always, give the correct ordering between 2 sublevels that both have electrons. The idea that we have to consider the effects of the interactions of charged particles in an atom is a preview of the discussion we will have in our next module. By far the most important interaction is between the negatively charged electrons and the positive nucleus. But, as seen here, subtle effects from the interaction between electrons can play a role too. Really understanding Coulomb's law and how charge interactions affect energy will be a big help.